talked a lot about is Alfred Wegener. And if you remember about Alfred Wegener, he did not know exactly why the continents moved around like they did. He had a lot of evidence that stated that the continents did move, but he didn't have any real solid evidence as to why or how it did it. So today what we're going to look at is we're actually going to take a look at inside the Earth and see what's going on. We've labeled the different parts of the Earth. We've labeled the chemical side, which talks about the crust, the mantle, and the core. Then we also went over the mechanical side, which is the lithosphere, the asthenosphere, the mesosphere, the outer core, and inner core. Okay, boy. I was a little worried. Good thing you've got some notes there.
We thought you were just remembering.
I remember. Do you remember?
Remember what?
The layers of the Earth.
Oh, there's the crust, the center.
We just went over all this. Anyway, we're going to take a look at what's inside and why we know what's inside. But before we can get there, we've got to start 4.5 billion years ago when the Earth first formed. So the big question is this, and this is one of the things that we need to figure things out. Believe it or not, a lot of people think the sun heats up the Earth, and that's why we're all nice and warm and toasty here. That's not true. That's not true. Okay, the sun doesn't do that. In fact, when the sun is shining down on the Earth and we have this atmosphere, that sunshine goes right through the atmosphere and doesn't even do anything to the air. The air is transparent to radiation. There's only a few things in the atmosphere that it will actually do, like ozone. The ozone layer will block 95% of that stuff, so 95% doesn't even get here, and only the 5% does. Not. So the heat of the Earth, the way that we're warmed up is not by the sun, it's actually by the Earth itself. So the question we want to ask ourselves is where does the Earth, I would, get its heat? And we're going to look at two different things here. So like I said, we've got to start back 4.5 billion years ago. And we look at when the star and the solar system were forming. So we have the star sitting out here. And all around that star, we would have had a whole bunch of rocks and junk and debris. And that stuff was all over the place. So the Earth is going around in this field of debris. We know what the debris looked like because that's what the asteroid belt looks like. It's also what the Oort cloud looks like. But a lot of that stuff is gone. And that's because as these particles or these great big objects start moving around, they're going to collide into each other. And as they collide into each other, they're going to actually form larger and larger objects. And when they do collide into each other, they're going to cause a lot of heat. And we call this the heat of formation. The heat of formation is when these objects start colliding into each other and they're going to form a lot of heat. So we have this mini Earth. It's all it is just a rock out there. And it starts growing. And as it goes around the sun, what do you think it's going to do to all those little black dots that are going around and around and around? Yeah, it's going to collide into them, and it's eventually going to clear a path for itself. It's going to clean all this stuff out of its pathway. And we end up with an Earth. Okay? It's cleaned everything up. All of the stuff that was here is now part of the Earth. Mars did this, Earth, Venus, all the planets did this. However, we still have a remnant of this called the asteroid belt, which is between Mars and Jupiter. It's still there. What did the planet look like, guys? What did the planet look like when that happened? I mean, it's the same size as it is now. We'll just say it's Earth size. It's cleared everything out of its pathway. What does it look like? It's red. It's red. And why is the Earth red? Because it's molten. All the rock and everything out there has been heated up. It's really hot, and it's all molten. So now we have this planet here that is all molten rock. Lava, magma, it's glowing red. This is not a very good place to live. We've got a lot of clouds out there. We've got a lot of clouds that are not healthy for you. A lot of There would have been volcanoes. After this, though, this is just right at the very beginning where we get molten. Now, all of that heat formation is gone. Nothing else is really colliding into it. It's just starting going around. So there's no more heat being generated by all of this collision. So if there's no more heat, what's going to happen to this planet? It will start cooling down. And so what happens is when you get igneous or magma or lava, when it cools down, it turns into igneous rock. And in this case, it ends up looking kind of black. Gets this black shell on the outside of it, which would be basalt. And you end up with this really dark, metallic-looking planet. Okay, so you end up with this dark, metallic planet. It still has some cracks and fractures in there, and in between those cracks and fractures, you're seeing some glowing magma. But for the most part, it's starting to cool down. And it's been doing this ever since the beginning of the Earth's time. 4.6 billion years ago. This is still happening. We are still cooling down from that initial impact, but the heat that we receive from the Earth, part of it is from the heat of formation, and only 20% of the Earth's internal heat is from the heat of formation. Good question. Where is the rest? Okay. Where does the rest of it come? Because 20% is not enough to make life here possible. That's not a lot of heat. So we've got to change a few things here. So I'm going to give one of you an assignment. Let's say that, okay? I'll choose Bo. Okay? We give Bo an assignment. I have 20 great big beach balls here, and your assignment is you have to take them all at one time down to the office. So we load you up with these 20 beach balls, and here he is walking down the hallway, and he's very carefully holding on to them. What's the likeliness that you're going to get all 20 of them down in one trip? Okay, you might get like 3, maybe 4 if you're really lucky. 16 of them are probably going to fall off somewhere. Oh, yeah, they'll fall off. He's balancing 20 beach balls.
How big are they?
Regular old beach ball. Okay, it's probably not going to happen. Many of you have done this where you've had to carry a lot of stuff and then it just starts falling off. Okay, yeah, there he is. He's got like the big belly, and he's got one down between his knees, and he's doing all this stuff. But he's not going to make it simply because he can't hold on to all of those beach balls because you just don't have the capability of holding on to them. So what does this have anything to do with the Earth's heat? It has a lot to do with it. So take a look. Deep inside the Earth, we have a bunch of elements. There are a few elements like uranium, thorium, potassium. What else? Some other ones that are going to break down. And they act a lot like Bo with all of those beach balls. One in particular that we're going to look at is uranium. Uranium, when we look at uranium on the periodic table, it's number 92. That number has a very specific meaning to it. It's 92. Hydrogen is number 1. What do you think that means? Okay. Hydrogen has 1 proton. that means that uranium has 92 protons. That's why it's 92. So it has 92 protons. And the protons are positively charged. So it's 92 of them. We also know that it has 92 electrons also because it has to have the same number of protons. Otherwise, it won't be stable. Because electrons are negative, protons are positive, it makes everything nice and stable. But we don't count the electrons as far as its weight goes. When we look at the atomic weight, we don't add this into its weight because the electrons essentially just weigh nothing. So we don't count that. So we know we have 92 protons. What else is left? Neutrons. We've got to have neutrons in there. And neutrons have no charge whatsoever. They don't have any charge. Now there's another number on the periodic table that you'll see that's related to uranium, and it is a number that is pretty big. It's called atomic weight. And the atomic weight for uranium is 280 or 238. 238. What in the world does that mean? Well, if each proton equals 1 and each neutron equals 1 because they're both the same, then 238 tells us how many protons and neutrons they have together. That's its weight. So, how do we know how many neutrons we have? We take the number of protons, subtract it from the total weight of the atom, and we end up with 146. That's how many neutrons this thing has.
Wait, so there's 92 protons and electrons, right?
Yes. But we don't really count the electrons when we talk about weight because they really don't have any.
Okay.
But we do count the neutrons because the neutrons and protons are really about the same. Difference is their charge. Well, what happens with this is we know how much it weighs, 238, so we subtract 92 and we know how many neutrons we have. Now we know where all the weight comes from. But there's something wrong with this. Having 92 protons and 92 neutrons would be ideal, because then it would be like if I just gave you like 4 beach balls and had to take those down, you could probably do it. Okay, that would be like 92 and 92. But when we add more to it, that's like, oh wait, here's another one, and here's another one, and here's another. We could probably stack them all on top of you, but once you start moving, they're going to start falling off. This is the same way. Once we have a lot more neutrons than we do protons, then the element becomes unstable. That means these little guys just start falling off. And every time they fall off, picture this. If Bo was really to do that and we could actually treat it like a neutron, we would know exactly where Bo was going all the way down to the office. Because as he's holding on to that, and every time one falls off, you would hear this detonation. The little 7th graders would be like burned up into like this little twig. The kids down like putting their coins in the machine also. And it's like, what in the world? And the big flames like, well, there goes Bo. There goes Bo again. There goes Bo. Next thing you know, Bo's just taking them off and start hucking them at people. I mean, I can definitely see that, right? He's down there is like, where'd they all go? I don't know, I dropped them. Yeah, right. Okay, there's a lot of energy that is wrapped up into these things. Well, why are we talking about all this? Because deep inside the Earth, we have something going on that is called radioactive decay. And that's exactly what that is. Every time one of those neutrons fall off and go somewhere, it's decaying. And we call it radioactive because when it falls off, it releases a ton of radiation. And that radiation, once it is released out, turns into heat. And the Earth is heated by this. In fact, it's heated up so much that 80% of the Earth's heat is from radioactive decay. It is from radioactive decay. So we've been able to identify where the heat is coming from that heats up the Earth. 20% of it is from the heat of formation. 80% of it is from radioactive decay. So we know what's going on in the Earth. We know it's getting nice and warm. We know where all that heat is going to, but what else do we know? How do we know that there's a core in the center? How do we know that the Earth is made up of all these layers? How do we know that the Earth has a liquid center? This has to do with earthquakes. So we're going to take a moment here and talk about earthquakes for a moment. Earthquakes, when they take place, there's a lot of energy that is released. And when that energy is released, it is released in the form of seismic waves. I'm not sure if I did completely. Maybe. So seismic waves. There are 4 types of waves that are released when an earthquake takes place. One are body waves, and the other one is a surface wave. So out of the 4, 2 of those are going to be surface waves, 2 of them are going to be body waves. Surface waves do exactly what they say. They run across the surface. Surface waves are not very nice to people. They're the ones that are going to move the chandelier around. They're going to drop buildings. They're going to make your life not very fun. Body waves, we can actually detect body waves from one side of the globe to the other side of the globe because they can actually travel through the entire Earth. So we want to look at these body waves. The first wave is called a primary wave. The primary wave is also known as a P wave. It's just the shortened form of primary wave. And it's also known as a compressional wave. The compressional wave actually moves objects in and out. It's linear. When a compressional wave is traveling across the ground, if you have any objects in there, like these 2 little markers that I have, if they were pebbles in the ground and a compressional wave came through, these things would expand outward and they'd collapse back in. They get squeezed or compressed together. And they constantly are moving back and forth. I want to show you a compressional wave. They're pretty cool. And they are by far the fastest wave out of these first 2. So I can show this with a slinky here. Okay, it's kind of cool. You take the slinky and you can see that you have all these rings in here. What I'm going to do with the compressional wave is that part of this gets compressed. That would be a compressed section. And that compressed section will move all the way across the slinky. That's how compressional waves work. So the first wave is a compressional wave and they move very fast. So check it out. These are compressional waves. If you had an earthquake, this is what would happen. You would have one wave after another. And if you notice, the part that I'm compressing stays compressed as it moves all the way across, and the other part is not. It's stretched out. If I do one, you can actually see it go all the way across, and then it will actually start coming back. Oh my gosh, they went right through each other. It doesn't stop, they go through each other. So that's a compressional wave. That is the fastest wave. That's the first wave. You won't feel it. When it goes through, it will sound more like a freight train coming at you. You'll hear the ground, you'll hear it moving from one place, coming across the other one, but the ground doesn't really shake. It doesn't do anything because everything is being compressed. What do we know about it? We know it's the fastest of them all. It's the fastest compressional wave. Okay, it travels about 4 miles. Yep. The primary wave, the P wave, is the fastest. It travels about 4 miles per hour. Or per second. It is pretty fast. To go 4 miles every second, it moves pretty fast. Now, the other thing about this is that it can travel. Can travel through liquids. We know it can travel through liquids. The next one is called the S wave, or the secondary wave. And this is a little bit different. This is what we call a transverse wave. Now, you know what a transverse wave is. Everybody here has played with one, I'm sure. So this is a transverse wave. You take a rope, and all you need to do is just shake it. That is a transverse wave. Okay, it just goes up and down and up and down and up and down. They're a lot different than an ocean wave. An ocean wave actually causes things to rotate and roll. Transverse waves don't. They move up and down, but the particles are just moving up and down. So if we had these two particles in the ground, transverse wave came through, you would see this would go up, that would go up, and this would go down. And they just move up and down. This is the kind of stuff that when it happens, yeah, it will probably loosen up the mortar between the bricks. It'll probably make things fall off of the shelves. It might loosen up a few things, and things will fall off the ceiling. It's probably not going to make a building fall down. But it will definitely loosen things up. You'll feel everything just kind of jump up and down for a minute, and then it's gone. These are the transverse. Okay, they are not as fast. They travel about 2 miles per second. So they travel about half the speed that a primary wave does. And the other thing is they cannot travel through liquids. They cannot.
So if there's like a massive earthquake going on in the entire planet, in the ocean?
They won't go through the water. Compressional waves could. But this is key to how we know what the center of the Earth looks like. So I need to erase this. Can you erase it? We're good? All right, I'm erasing. So I'm going to draw 2 big circles up here. And they're going to be the Earth. We're going to look and see what these waves actually do when they go through the Earth. So, circle 1 and circle 2. Okay. Now, inside of it, what did we say was inside the Earth? There's a core. Is it liquid? Yep, it has a liquid outer core. And this is the same. This is also the core, and it is liquid. The outer core is liquid, solid inner core. Let's take a look and see what happens. So we're going to show you what a P wave does, and we'll also show you what the S wave does. So up at the top of the globe, we have an earthquake. Here's what the P wave does. The P wave can travel through liquid, so it will go straight down. But when it comes in on an angle, it doesn't do that. Because it's going through a liquid, it will act a lot like light does when it goes through water. So you see the straw, it goes through the glass, it bends or refracts, hits it, comes out somewhere else, and then it gives you the impression that the straw is somewhere else instead of where it actually is. So when this comes in, it will actually bend inward, and then it bends again. But it does eventually make its way out. Same as over here. It comes in, bends out, it comes in over here. Over here, it totally bypasses that completely. And because it's going through a material, and it's going to refract. Okay, it's not going to follow this a straight path all the way. Now, interesting thing is that this does not show up right here. The P wave, the primary wave, does not show up between 104 degrees and 140 degrees. It's totally voided right here, and we call this the P wave shadow zone.
That's parts of the Earth that are like earthquake resistant?
No, they just never show up. You can sense it anywhere around here and anywhere right here.
There's an earthquake there. It still happens.
It does.
It
Ish, from this point on over 104 degrees and 140 degrees. In between that gap, they just don't show up. That's a clue.
But if you were standing there, you'd still feel it?
No, not right there. You wouldn't. You would have no idea. But if you were in between these areas, you would be able, if you had a seismometer, you'd be able to detect it. You yourself probably would not detect this because they would be faint. But you can't hear, and the reason being is because as it comes through here, none of these waves are actually refracted into that area. They cannot make it there. The other thing is, let me show you what happens here with the S wave. It doesn't go through a liquid, so what does it do? It doesn't even make it there at all. So when we get to this point, at 104 degrees on either side, that is totally void of the S wave. And we call this the S wave shadow zone. Why does this even matter? It does matter. This is how we know that the center of the Earth has a liquid core. We know in order, if this didn't have a liquid core and it remained the same, we should get lines right in through here. Everything should be these nice little lines, but it isn't because they get refracted. This one should show up over here, but it doesn't. Instead, it gets bent inward and then it shows up here. This one should be over here, but it doesn't. The only way that can happen is if it has a liquid core. The only reason why none of these S waves show up here is because there's got to be a liquid core. They cannot pass through liquids. And even by looking at this, we can identify how big the core is. Take a little math, you figure it out, get to this point and this point. You do the same thing over here, and we can actually figure out what the size of the core is. We know it's roughly the size of Mars. This is how we know what the center of the Earth looks like. We know it has a liquid core because these waves cannot pass through the liquid center at the same rate that they normally would, or they just can't, period, because they are not capable of going through liquids. Now, when we get all this stuff done, now we know where the heat is. We know what the Earth looks like. There's a few more things we want to look at. We know that heat is going to be released, and as it's released, it's going to cause the mantle to start moving. Things are going to be more liquid. Things are going to start flowing. The mantle starts moving. We get a thing called convection currents, and those convection currents are going to start help moving the crust. Just like if we had a whole bunch of conveyor belts or treadmills, they're running, you walk on it, you're going to go along with it. If the center of the Earth is moving around, then we can expect the outer core or the outer crust to move along with it. And this is where Wegener, he didn't have any idea about any of this stuff, but we do now. The next time we talk, we're going to talk about the boundaries and the different plates and how they move and what happens to the crust and why we have earthquakes, volcanoes, and mountains and all that other good stuff. Sound good? Sounds wonderful. All right. Awesome.